And the inverse function theorem says that we have a neighborhood or an open set containing AB in this space, and another open set containing A0 in the right hand side space, such that G is a so-called diffeomorphism of these two open sets, between these two open sets. Then our Pc, we take this Pc to be the inverse of G, local inverse of G. Okay, because G is a bijection from this open set in the right hand side, left hand side to the open set in the W in the left hand side. Now our Pc here is precisely the inverse of G. Therefore, Pc is defined in W. Of course, because we don't need to mention the open set here on the left. Therefore, we simply say that our Pc is mapped into U cross V. Okay, so we don't need to mention this set. We will not draw it in here. Okay, so this is U. This is U cross V. Okay, now our AB is an interior point of the image of W under Pc. Actually, the image of W under Pc is open, and obviously AB belongs to the image. So because of this reason, there exists an open set containing A. We denote it by O1. And also another open set, omega, containing B. In Rn, we denote it by omega, such that the clause O1 clause omega is a subset of the image of W. Okay, so this is also obvious. We have obtained an open set here of A, and also another open set of B containing B, such that this is O1 cross omega. This is O1. This is omega. This is contained in the image of W under Pc. Now, from the definition of our map G, what we get? By the definition of our G, if xz is a point in W, then the first component of xz must be x. Why? Why this is true? You see, Pc xz is Pc1 xz, Pc2 xz. The Pc1 is n-dimensional. Pc2 is n-dimensional. But Pc is a local inverse of G. Therefore, xz is G Pc xz. But since gxy is x capital F xy. Okay, so this G is precisely G Pc1 xz, Pc2 xz. So by the definition of G, this must be Pc1 xz and Pc2 and the capital F. And this part, we don't care what it is. We don't care about the last n component of this. But here x is n-dimensional, z is n-dimensional. Here Pc1 is also the n-dimensional part of the image. Therefore, comparing this, we conclude that x is psi1 xz. So this proves our conclusion that psi1 xz is x. So our psi can be written as psi xz is x and psi2 xz. It has this special form. Okay, now we take O to be a subset of O1. O consists of those x in O1 such that x0 belongs to W. This is our O. So O is a subset around A in here. This is our O. Okay, and it has a copy. It's a subset of O1. So this is our O. Okay, we take this O. Obviously, this O is open. It is not difficult to see that O is open and containing the point A. Therefore, O belongs to open set containing A. O is an open set in Rn containing A. Therefore, by our notation, it belongs to this NAN. Okay, and then we defined our map phi, which is the psi2. The phi is map x to psi2 x0. We let phi to be this map. Then phi is a map from O to V. Define this map in this way. The second component of psi, that is psi2 here, depends on x and z. We fix z to be 0. Then it is a map of x. This map we call it psi. We call it phi. Phi. Okay, we call it phi. We will see that phi is the map we want because we have this computation. X capital F x phi x. Then this is by definition of G. This is precisely G x phi x, right? This is the definition of G. Then this G is x. Phi x is psi2. Sorry, I'm missing a G here. G, we copy G here, but X also copy. But the phi X by definition is the psi2 x0. Okay? The X phi X by the definition of phi X is psi2 x0. Okay? I emphasize this by phi X is psi2 x0. Okay, so we have this equality here. But x phi 2 x0 is precisely G psi x0, right? By the definition of psi, by the analysis of psi, we also know that the first m component of psi is identity map. Is x here. Look at the equality on the upper right corner of this page. Here, psi1 xz is x, and the psi is psi1 psi2. Therefore, this x here, look down. This x here is precisely psi1 x. Of course, you can also call it psi1 x0. Okay. Therefore, together is the Psi at the point x0. So we have this equality. But now G and Psi are inverse to each other. Psi is the local inverse of G. So their composition is the identity map. So we conclude that this is x0. So from this equality, you compare, you take the last n component of this equality. What equality? X capital F x phi x is x0. So we conclude that f x phi x must be 0. So this map phi should be the map we want. We prove that we can have a map defined in an open set containing A, that is our O, that is our this map. We have obtained a map such that for x in O, for every x in O, fx phi x is 0. So this is the second conclusion of the inverse function theorem. Okay. We also need to prove the first conclusion and the third conclusion. But we're almost done because the most difficult part already been overcome by us. Okay. So next, what should we do? Having obtained this map phi, we can easily conclude our proof. So for x in O, our x phi x is x psi 2 x0. That is psi x0. Okay. So we take x to be A. What should I obtain? Let x equal to A. Then A phi A is psi A0. Psi A0 is AB. Okay. So this implies that phi A is B. So this is the first conclusion of our theorem. Okay. That is the function, the graph of the function passing the point AB. Okay. Now, we prove the uniqueness. The uniqueness, that is the third part of the theorem, by continuity of phi. Phi is obviously C1. Phi is C1 because psi is C1. Phi x is psi 2 x0. So psi is C1. Therefore, psi 2, the second component of psi is also C1. So let's check the z equal to 0 as a function of x. It is also C1, continuously differentiable. So phi is continuously differentiable, of course, continuous. We can take a smaller psi. For smaller, we shrink small a little. Smaller. The open set containing A, we shrink this open set O slightly. We can assume that any x in O, we have phi x belongs to omega. Okay. Why this is true? Because phi A is B and phi is continuous, at least at A. Okay. Therefore, when x is very close to A, phi x should be very close to B. This is the continuity. But phi x is very close to B means that phi x is contained in an open set containing B. That is our omega. Okay, so this is the usage of continuity. So having obtained this, then G is injective. We remind you that G, of course, G is U cross V to Rm cross Rn. But G is injective over O cross omega. Why it is injective? Because our psi is a local inverse of G. So in the whole U cross V, G might not be injective. You might have different 2 points in U cross V. Their image under our map G are the same point in Rm cross Rn, Rm plus N. Okay, but restrict to a neighborhood of AB, because G, by the inverse function theorem, G is a local diffeomorphism from the point AB to the point A0 here. So near AB they are injective. G is injective. Okay. So since G is injective in this O cross omega, then we also know that for X, if a point X, Y in O cross omega is such that capital F X, Y is 0, then our GXY is X0. By the definition of G, GXY is X0. But we also know that Fx Px is also 0. Okay, so this GXY can also be written as Gx Px. So G is injective. The injectivity of G means that xy equal x Px. Therefore, y is Px. So this proves the third statement of the inverse implicit function theorem. Okay, so this completes the proof of our important theorem, the implicit function theorem. Okay.